Hello everyone, and welcome to Jam Academy. The objective of this problem is to help you know how to apply the work kinetic energy theorem in a system involving springs and friction. So this is quite an interesting and a very important problem, so stay tuned and pay attention. A block of mass m is moving with speed v0 along a horizontal surface towards a spring with force constant K that is attached to a wall as shown. The spring has negligible mass. Now we are required to calculate the maximum distance d the spring will be compressed if A, the surface is frictionless, and B, the surface is rough with a coefficient of friction mu. So we have two scenarios here. The first case is when the surface is frictionless, and the second case in which the surface is rough. It doesn't matter what case state, we're going to apply the work kinetic energy theorem, and I'm going to show you how fun is it to apply the law. The very first step is identify two crucial points, the initial and the final point. Always start by identifying the initial and the final point. Now, right here, I'm going to take this as my initial point, and I'm going to take this right here as my final point. This is B. So what do we know? We know that the net work done on the object is just going to be equal to the change in the kinetic energy of the object. By that I mean is the kinetic energy at B minus the kinetic energy at A. So the question I want to ask you is, what is the kinetic energy at A and what is the kinetic energy at B? Now the kinetic energy at B, obviously at B the object comes to rest. So the object is momentarily at rest, which means that the kinetic energy at B is 0. So this is 0 minus 1/2 m v0 all squared, because the speed of the object at A is v0. So the next question I want to ask you is, what will be the net work done in the absence of friction? In order for us to calculate the net work done, it will be helpful for us to draw a free body diagram. Now, if I draw a free body diagram, this is mg. There is no friction in this case. This is N. Now the force in this direction, this is F sub spring. That is the spring force, capital F of S, which is given by Hooke's law. Now, that being said, we can therefore calculate the net work done on the object. So the net work done on the object, remember that the displacement is to the right, but the spring force is to the left. So what that means is that the net work done on the object will be negative. So this will be negative the integral of Fs dx, and we are integrating from 0 to d, which is equal to negative the integral of kx dx from 0 to d. Now remember that Fs is equal to kx. This is essentially Hooke's law. That is essentially Hooke's law. We dwelled with that before. So this will be equal to negative 1/2 k x squared from 0 to d. So the external work done will be equal to negative 1/2 k d squared. And if this is true, we can therefore see that this will imply that negative 1/2 k d squared will be equal to negative 1/2 mv0 squared. The 1/2 will take care of each other, which would mean that d squared will be equal to m over k multiplied by v naught squared. If you want, you can leave it this way, but I will further simplify by taking the square root of both sides. This will mean that d, in the absence of friction, will be equal to v naught, the square root of m over k. And this will be my answer for part A of the problem. This will be my answer for part A of the problem. Now, what will happen if friction is present? What will happen if friction is present? That is a very good question. How will our solution be affected in the presence of friction? Remember, fellas, that the kinetic energy, the work kinetic energy term says that the net work done is equal to the change in the kinetic energy. I cannot overemphasize that particular statement. Now, the total work done, which is the net work, is equal to the work done by friction plus the work done by the spring. We have already calculated the work done by the spring. So the question is, what is the work done by friction? To do that, we need to know the friction force. The work done by friction, which is static friction, remember static friction Fk is equal to mu k multiplied by n, which is equal to mu mg. Because in this case, n is equal to mg. This would mean that the work done by friction is equal to the friction force multiplied by d cosine theta, which is equal to the friction force is mu mg multiplied by d cosine 180 degrees. So this means that the work done by friction will be equal to negative mu mg d. This defines the work done by friction. Hence, the total work F net will be equal to negative 1/2 k d squared negative mu mg d. This right here is the net work done on the system in the presence of friction. Now, by the work kinetic energy theorem, we can confidently say that 1/2 k d squared minus mu mg d will be equal to 1/2 mv naught all squared. Now it is left for you to make d the subject of the equation. We can multiply throughout by negative sign and bring the term that contains 2 to one side of the equation. If we do that, we will have, or let's first of all multiply throughout by 2, we will have k d squared plus 2 mu mg d minus mv naught squared, all of this equal to 0. Remember, this is like a quadratic equation. And if you have a quadratic equation, let me just remind you, ax squared plus bx plus c equal to 0. This means that x is equal to minus b plus or minus the square root of b squared minus 4ac all divided by 2a. So we're going to use that to calculate d. We have here d squared plus 2 mu mg over k d minus m v naught squared all divided by k. All of this should be equal to 0. This means that a is equal to 1, b is equal to 2 mu mg over k, and c is equal to negative mv naught squared all divided by k. So our job right now is to substitute the value for a, b, and c in the equation to solve, in the formula to solve a quadratic equation. And if we do that, we will end up with d equal to negative b, which is 2 mu mg over k, plus or minus the square root of b squared. This is 4 mu squared m squared g squared over k squared, minus 4a, which is 1, c, which is m squared v naught squared all divided by k squared all divided by 2a, which is 1. This is a mess, but we're going to simplify. So we have here negative mu mg over k plus or minus. We can factorize the terms that are constant. You have 4m squared over k squared constant, so this is like 2m over k, the square root of what is left in there, mu squared g squared, mu squared g squared minus v naught squared. So remember that d has to be positive because d represents distance, and if that is the case, d will be equal to so remember that d is positive, which would mean that d is equal to mu mg over k minus plus the square root of mu mg over k, all plus, this is plus, mv naught over k all squared. This will give us the value for d. Now the problem in the second part gets a little complicated algebraically, but you get the point. Now all you have to do is calculate the net work done on the system and then equate that to the change in the kinetic energy of the system. Then you can use that expression to calculate whatever you are required to calculate. Thank you so much for your time, and if you have any problems or difficulties with this particular problem, please ask your questions in the discussion forum below this video. Remain blessed, and thank you. Bye-bye.